All right, welcome to Chapter 2, Optimization Basics. Whether or not you are a pro at optimizing power markets, I recommend you at least peruse this section to get comfortable with the visual design we'll be using and all of the examples in this presentation, get comfortable with the terminology that I'll use, and maybe you'll learn something and maybe you'll just get better at optimizing. So looking ahead to chapter 4, that's where we hit peak complexity in this presentation. We're going to be figuring out what resources are economic for dispatch and which resources we attribute to a GHG area. We'll determine how to set prices and discuss how price formation with GHG relates to basic price formation principles, and figure out if those prices are efficient. So before we get there in this chapter, we're going to review all of those concepts, figuring out how to dispatch resources at least cost, how to set prices, and what efficient prices means. And we'll do that without GHG. I've also put a few links in the appendix to the ISO's Learning Center if you'd like some additional resources to better understand these concepts. First, some basic terms and concepts in this presentation. The big one is locational marginal prices, or LMP. Resources respond to this price signal. They respond to their locational marginal price, the price at their location. And this price signals the marginal cost of the next increment of capacity needed to meet load at that location. So I'll show you how to figure out what the LMP is in each area that we look at. The next three terms, I think it's easy to confound when we talk about a specific resource, so I wanted to make a distinction between these ideas and establish a regular convention for this. Some people say bid price, marginal cost, and we're also going to talk about the total cost of a resource. A resource's bid price, that's the bid that they submit to the market, traditionally or typically represents the cost of incremental capacity from that resource. And some people will say the bid price is a resource's marginal cost. That might not always be the case. You can bid whatever price you want into the market. So I'll be referring to a resource's price as its bid price. The total cost of a resource is the aggregate cost of capacity, or the cost that the market needs to cover in order to dispatch these resources. So for example, if a resource bids $10 per megawatt hour, that's the bid it submits to the market. That likely represents the incremental cost of capacity from that resource. If we dispatch it to 10 megawatts, the total cost of the resource is $100. Finally, I'll talk about surplus quite a bit in this presentation. We'll identify surplus payments, which is some level of profit that inframarginal resources receive. So inframarginal resources are resources that have a bid price below the market clearing price, and they receive a surplus payment that signals the value of these resources in the market. So I've illustrated some of these terms here. $30 per megawatt hour on this image is the market clearing price. That's the red dotted line. And that's the LMP, basically, for this market. This is the LMP that all of the resources in the supply stack on this screen respond to. And as we discussed on the previous slide, resources are paid the marginal cost of meeting the next increment of demand. So on this image, we need to meet 400 megawatts of demand. The 401st megawatt, let's say, costs $30 per megawatt hour. So the market clearing price is $30 per megawatt hour, and all dispatched resources are paid $30 per megawatt hour. The bid price of resources in this supply stack range from about $10 to $30 per megawatt hour. And so if you look at those $10 per megawatt hour resources, those are reducing the total cost of operating the system compared to the marginal resources. So they receive a surplus award. They receive extra revenue for reducing the cost of the system and providing that value. And this brings us to some common price formation principles. It's really only one with a couple of click downs. The big idea here is that prices should provide a sufficient incentive for resources to follow their dispatch instructions. For example, the marginal resource that sets the price should make $0 in profit and is indifferent to dispatching across its operational range. If you're making $0 in profit, you don't care if you put 50 megawatts onto the grid, 100 megawatts on the grid, no megawatts onto the grid. In any case, you make the same amount of money. Resources that are able to dispatch at a relatively lower cost than the marginal resource should have an incentive to dispatch to their full capacity. And the surplus revenue that they receive, you can think of that as the signal for investment that says those inframarginal resources are going to make money at that time and at that place. So I'll go through a pretty simple example, but this is the basic layout that you'll see in all of these examples in the presentation. As it gets more complicated, I'll shift things around, but there are some common features here that I want to point out. First, on the y-axis, you've got prices in dollars per megawatt hour. I've also put the bid price of each of these resources on top of the resource. So Unit 1 bids $30 per megawatt hour into the market, Unit 2 bids $35 per megawatt hour into the market, and Unit 3 bids $50 per megawatt hour into the market. The width of each of these resources represents their capacity. Units 1 and 2 are both 200 megawatt resources. Unit 3 is a 300 megawatt resource. For this Evergreen training, this aspect of the visual design is mostly just visual design because we're making a few simplifying assumptions. But as we add complexity to these examples, you'll see that being able to identify how much of the resource we have available will become important. So back to the original question, how do we dispatch these resources to meet 250 megawatts of load? Well, we'll go in least cost order, and we can figure this out just by eyeballing it. So the least cost resource is Unit 1, that costs $30 per megawatt hour. Then we still need 50 additional megawatts. We'll take that from Unit 2, and that is sufficient to meet load at 250 megawatts. And I've summarized this in the box at the corner of the slide. Now, how do we figure out what prices will incentivize 250 megawatts of supply to dispatch onto the grid? We figure that out by looking at what we need to meet the next increment of load. So let's say 251 megawatts of load. The 251st megawatt of load we would take from Unit 2, and that costs $35 per megawatt hour. So the LMP, the market clearing price here, is $35 per megawatt hour. In technical terms, what we're doing here is looking at the shadow price of the power balance constraint. But in all of these examples, what we'll do is we'll just look at what happens when we increase load by 1 megawatt in each area. So I've updated the box in the corner of the screen that shows you that Units 1 through 3 all respond to the LMP of $35 per megawatt hour. So now let's see if this price is efficient, if it fulfills our principles of incentivizing least cost dispatch. Unit 1, which is the least cost resource, meaning it actually reduces the total cost of the system, receives a $5 per megawatt hour surplus from the LMP. And that signals the value of this resource to the market. It has a sufficient incentive to dispatch to its full capacity. If it only dispatched to 100 megawatts, it would lose out on $5 per megawatt hour profit. Unit 2 makes $0 in profit per megawatt hour, so this resource is indifferent to dispatching across its operational range. Finally, Unit 3 would lose $15 per megawatt hour if it put any of its capacity onto the grid at this clearing price. So it has no incentive to dispatch. The market is signaling that we don't need it, and therefore this price is efficient. So we're going to add another layer of complexity here. We want to figure out how to account for load in two separate areas, and we'll add a physical transmission constraint. In the previous example, we had a single LMP, and when we figured out what that LMP was, we added 1 megawatt to the full market, 250 megawatts. But in the next example, and in the rest of the examples in this presentation, we'll have two separate areas with load in each area, and we'll have two separate LMPs. If we had unlimited transmission, a single resource in any area would be able to set the market clearing price. But if those two separate areas have separate GHG preferences, then we might still see a difference in LMPs. So different LMP, or the difference in LMPs, can come from a transmission constraint or separate GHG preferences. So in order to understand when we're seeing a price difference due to GHG, I wanted to start out by walking through how a transmission constraint creates price separation. That way we'll be able to differentiate what these price signals are saying once we have both in the same example. So this looks a little bit different from the example we just walked through. Some similarities: you still have prices on the y-axis. I still put the bid price on top of these resources. Their width tells you the capacity. But now we have two separate areas, and I've labeled them here balancing area 1 and balancing area 2. We have one resource in balancing area 1. It's a 300 megawatt resource, and it has a bid price of $50 per megawatt hour. In balancing area 2, you've got two resources, units 2 and 3. They are both 200 megawatt resources. They cost $35 per megawatt hour and $30 per megawatt hour, respectively. And I've labeled load for each area on the bottom. So in the green box, it says L1, that's load in balancing area 1. So in order to meet load in balancing area 1, we need 200 megawatts. And then in order to meet load in balancing area 2, in that blue box, we need to meet 50 megawatts. These two areas are separated by a transmission constraint. And the transmission constraint here is a 100 megawatt transfer constraint. So that means this transmission line can only hold net 100 megawatts. And I'll show you what that means in a moment. So before, when we didn't have this transmission constraint, we would try and serve all 250 megawatts of demand by going in least cost order. So let's try that. The least cost resource is unit 3. We dispatch that whole thing up. The next least cost resource is unit 2, and we'd take 50 megawatts of that. But now we have a problem. We can sink 50 megawatts into L2, and that means we have net 200 megawatts coming out of balancing area 2. But we can only transfer 100 megawatts of that to balancing area 1. So this tells us what our constraint is. It's how much load we have plus this transmission capacity. So we can only actually dispatch up 150 megawatts from balancing area 2. What that means is the last 100 megawatts we need to meet load are going to have to come from unit 1. And so I've highlighted that here. In order to meet load at least cost, what we'll want is 150 megawatts of unit 3 at $30 per megawatt hour, but then we hit our constraint, And the next least cost resource available is going to be Unit 1 at $50 per megawatt hour. Now, how do we set prices? We can already see that there's going to be price separation because we don't need all of Unit 3. So if we price the whole market at, say, $50 per megawatt hour, we'll have a problem. The price signal will say that both Units 2 and 3 are economic when actually we don't need all of their capacity. So let's go area by area. In balancing area 1, we currently need 200 megawatts. To figure out what the clearing price is in balancing area 1, we'll increase load there by 1 megawatt, or in technical terms, we'll relax the power balance constraint and see what the shadow price is. So in order to meet the next megawatt of load in balancing area 1, we'll take that from Unit 1. Remember, we've already met our constraint in balancing area 2, so the next cheapest resource that we can physically get to meet load comes from Unit 1. Now let's check out balancing area 2. If we increase load in balancing area 2 by 1 megawatt, we can actually take that next megawatt from Unit 3. Remember, what we can dispatch up in balancing area 2 is the load plus the transfer constraint. So now we can dispatch up 151 megawatts from Unit 3, and that 151st megawatt is $30 per megawatt hour. So I've just summarized what we just went through on the screen, so that you can come back and refer to this if you need to confirm or verify what we go through in Chapter 4. The LMPs can be verified by increasing load in each area. If we increase load in balancing area 1 by 1 megawatt, that incurred an additional cost of $50 per megawatt hour to the whole system. If we increase load in balancing area 2 by 1 megawatt, that incurred an additional cost to the system of just $30 per megawatt hour. And that is how we set our prices. So the LMP in balancing area 1 is $50 per megawatt hour, and Unit 1 responds to that price. The LMP in balancing area 2 is $30 per megawatt hour, and Units 2 and 3 respond to that price only. And I've summarized this in the gray box above. Is this efficient? We only need 100 megawatts from Unit 1, which means it makes zero profit, and it's indifferent to operating across its operational range. Unit 3, we only need 150 megawatts from, so it makes zero profit, and it is indifferent to dispatching across its operational range. So what does the difference between LMP1 and LMP2 mean? That's going to tell us what the marginal cost of congestion is. Technically, the marginal cost of congestion represents a real cost that Unit 3 would incur if it tried to put more capacity onto the grid than the constraint can handle. It would actually have to pay that price. And this prevents resources from chasing the LMP at other locations when there's a physical constraint. But for the purpose of this presentation, we're going to talk about the marginal cost of congestion as a shadow price of the transfer constraint. So just like we did to find the LMPs, we will increase the transfer constraint by 1 megawatt to verify what the marginal cost of congestion is. When we do that, we're able to dispatch an additional megawatt from Unit 3 and dispatch down one of the more expensive megawatts from Unit 1. And that saves the whole system $20. So your marginal cost of congestion in this example is going to be $20. And I've summarized that here for you. marginal cost of congestion can be verified by relaxing the transfer limit by 1 megawatt, and then we resolve optimal dispatch and see what that saves to the system. This is the last slide in optimization basics. In chapter 3, we're going to build on these concepts by introducing GHG, figuring out how to find the marginal cost of GHG, looking at the difference between transmission constraints and LMP separation due to GHG, and then we will be set to go through the examples and the business practice manuals.